Hey everybody, I want to tell you a little bit about functions and relations. So functions are a really important idea that we're going to need to use a lot. So let me go ahead and start up a whiteboard here. So the idea of a function, well, actually, let me talk about relations first. So the idea of a relation is it's any set of ordered pairs, really. It's any way you can pair up one set of numbers with another set of numbers. That's really all a relation is. Basically, anything you can graph is a relation. So for instance, I could do like, so let's say I have this graph here, right? And I put a point there, and let's say that's the 0.53. By having the 0.53, what you're really saying is I have some thing that relates an x value of 5 to a y value of 3. And whatever that thing is, that's a relation. That's all a relation is it's a way to map x values onto y values and vice versa. That's all it is. That is a pretty general definition, and it's not necessarily a thing that we're going to use a lot. What we're going to be more interested in is functions, which are a restriction on that. So while a relation is any way to relate some set of x values to some set of y values, or one set of points to another set of points, a function is best thought of as a machine. So for instance, here, let me draw my standard function machine. It's like this. I'm going to call this machine is called f. And it takes in a value, and then it does something to it. It does f to it. And then it outputs the result. So usually what we say is it takes in an x value, and we do f to it, and then it outputs the result of that we call f of x. Now, that's just another name for y, right? The idea here is that we take in an x, we take in an input, we output a y or an output. And the thing that does the operation, it's called a function and it's called f. Now, you might say to yourself, that sounds an awful lot like what you just said about relations. How is that different? And the way that it's different is that f is much more like a machine in that if it takes the same thing in, it will output the same thing every time. So I like to think of it this way. So I want to think of Santa's workshop, right? So Santa has modernized and he doesn't have just elves anymore. Now he's got machines that make a lot of stuff. And he's got this special machine that takes in, let's say, a piece of wood and outputs a little wooden train. The ones you always see in the idyllic Midwestern Christmas stories, right? So Santa's machine. Santa's train machine. Wood. Roop. Roop. We're going to call this, by the way, T for train. So you put in wood and you output T of wood, which is a train. Now, if Santa wants to output something else, he's going to need to use a different machine. He can't put a piece of wood in here and get a little wooden rocking horse out of this. This thing only makes trains. This is a function because anytime you put in wood, you get out the same thing, right? Like functions are consistent. They give you the same thing every time if the same input gives you the same output. So if you get one input giving you two different outputs, like Santa puts a piece of wood into a different machine, right? So this is going to be called R. This is the random machine. Random machine R. Here, this machine takes in wood, and it outputs a variety of things. Train. Sometimes you get a train. Sometimes you get a little rocking horse. Sometimes you get like, let's say, a workbench for Dad. Sometimes the machine just goes haywire and gives you a bunch of dust. This is a relation. This can take in one thing and give you out a variety of different things, and functions cannot do that. Functions only do one thing. Functions are a very simple, straightforward machine that take in something and put out the same thing every time it takes in that one thing, right? So this machine takes in wood, puts out trains, that's it. This machine takes in wood and puts out a variety of stuff. You don't really know what you're getting. It's random. So this guy's a relation. This is a relation. And I'm being a little unfair to relations here. They're not random, right? They put out only a few different things, usually. But that's the essential difference between the two, is that a relation can give you out a variety of things for even a single input, right? You put in the same thing and you don't necessarily know what you're going to get out, as opposed to a function where you put in something and you know exactly what you're getting out. Now, okay, that's enough cute examples of Santa's workshop. Let's see how this looks on a graph, because that is where we're going to want to, that's where we're going to be using this, right? So here is what happens with a function. The inputs are x's inputs, and the outputs are y's outputs. So let's say this input here, I'm going to make this better. This input right here, boop, gives that output, right? Now, what I can't have is that same input giving me a different output. I can have that particular input giving me that output every time, but it can't change. So we're okay here. This is a function because that input gives me the one output. Similarly, if I have a different input, I'll get a different output, right? So each one of these different inputs gives me its own output. The outputs can be the same as each other, but the inputs can't be. This stops being a function when the same input gives me different outputs. This is a problem, right? This thing is not a function here, because I've got this one, here, let me change the black here. I've got this one input that gives me two different outputs, and it stopped being consistent. There is at least one value where I put in something and I don't know what I'm getting out. Could be one thing, could be the other thing. That's not a function anymore. It's not necessarily a problem. Like relations are a fine thing, but it's not a function. So what that means is, for our purposes, that's essentially what a function is. It's a thing that when you put in something gives you out the same thing every time. Okay, so this guy's a function. Let's do this. So function, as opposed to something like this, where, oop, that's not what I meant to do. Let's try it again. I want to make that red. Where I can get different outputs from the same input, right? So this is, I don't want to say it's a problem, but this is not a function. This is a relation because it's a set of points. Like I said, any set of points is going to be a relation. But these three right here that all fall on a vertical line, this is a relation. So functions are super important because they're basically how we build mathematical operators in general, right? Sometimes we use relations too, but for our purposes in this class, it's going to be functions. So we want things that are consistent, where we put in something and we get out the same thing every time. So let me give you a couple of examples of of functions versus relations. So functions. Something like, let's say, f of x equals x squared, or g of x equals 2x minus 1, or h of x equals absolute value of x, 3 times absolute value of x plus 4, right? Those are all perfectly legitimate functions because whatever I put in for x, I'm going to get out the same thing every time. If I put 2 in for x here, I get 4. If I put 2 in for x again, I don't suddenly get something else. It's still 4. Relations, on the other hand, don't necessarily do that. And I can't write relations in this same way. This right here is called function notation. Anything you can write like this is going to be a function. So I have to write these a little bit differently. So something like y squared equals x, right? That's a relation where my inputs are x and my outputs are y's. Or absolute value of y equals 2x minus 3. Basically, you're going to have to do something to y in order to get something that's not a function. It's actually pretty hard to come up with these things. I can graph them easily enough. Here's a good one. X squared plus y squared equals 1. That, if you don't know, that's a circle, if I were to graph that. So these guys are all relations. Now, all of these are relations as well, but they're also functions. So what we have is a relationship like this, where relations, and then inside of that, you get functions, right? So functions here. I draw it like this to sort of demonstrate that relations are the wider category, and then a subcategory of that is functions. So every function is a relation, but not every relation is a function. Sort of like, let me use even numbers and all numbers, right? So all natural numbers, 1, 2, 3, 4, 5, up forever. That's a larger category, and then even numbers are within that, right? So 0, 2, 4, 6, I don't know if I said 0 before, but 2, 4, 6, 8, 10, those are all numbers. So all even numbers are numbers, but not all numbers are even numbers, right? So there's something contained in a larger category, or like, all pianos are musical instruments, but not all musical instruments are pianos. That sort of thing, right? This is the relationship that you get. A function is a kind of relation. It's just got that extra restriction that makes it consistent. So the thing I want to mention here is function notation. So function notation looks like this. This turns out to be super useful, but it takes a little bit of getting used to. A lot of people have trouble kind of grasping the idea of function notation, but all it is a way to remind ourselves what we're putting in, what we're getting out, and what our operation is called. That's all it is. So here's we'll start with a simple one. F of x equals 2x plus 3. Okay, so this guy is the input, also called the argument. Not sure why, but that is what it's called. And that x that I've circled in red is also this x that I've circled in red. Whatever goes inside the parentheses by the f is what goes in the variable in the expression. So for instance, I might say f of 2 to specify that when I put 2 into f, I get, well, what's 2 times 2 plus 3? Oop, that last one shouldn't be parentheses there. I didn't mean that. Is 7. So I would say this, f of 2 equals 7, right? So this tells me that here's the thing I put in, here's the thing that I got out. So a thing that people get often messed up by is the idea that this is not 2. That thing that I circled is 7, because that's the output. The name of the output is f of 2, right? So here's my function, my little box. So in this case, I put 2 in, and I got out 7, right? So this is x, and then we do f to it, and we get out 7. So f of 2 is not 2. F of 2 is 7. 2 is just the input. This expression right here is equivalent to saying, to having this ordered pair, 2, 7, right? When I write this ordered pair here, what I really mean is, if I put 2 into my function, the thing that I get out is 7. And then I would graph that like this, right? I would graph that point here, right? If this is 2, 7. So all of these are saying the same thing. This says my input's 2, my output's 7, my function's called f. This point said, or knowing that this is an ordered pair, says, well, if I put 2 into whatever my operation is, the thing that I get out is 7. On a graph, it looks like this, that says where all the inputs are on the x-axis. That says that if I put in 2 here, that the thing that I get out is 7, right? That's another way of looking at it. It's just a visual way of saying the same thing. So these are all the exact same idea, and function notation, like this is function notation. This is just standard function notation here, saying what's the name of your operation, whatever you're calling this thing, that has to show up over here, right? This is the name of your variable. This is, by the way, called a dummy variable, in the sense that you can call it whatever you want. If I said f of t is 2t plus 3, that would be exactly the same idea. There's literally no difference there. If I said f of a equals 2a plus 3, or anything like that, those all say the same thing. It doesn't matter that my variable is called x. We usually call it x, but you don't have to, right? So if I have f of x equals 2x plus 3, f of t equals 2t plus 3, f of alpha equals 2 alpha plus 3. My favorite one, f of smiley face, is 2 smiley face plus 3. Right, whatever's in the parentheses is what appears in the output with these operations of times 2 and plus 3 done to it. So that means that we can do things where plus and times are defined without them having to be numbers, right? So we're going to return to this in a future video. I think maybe the next one. I'll have to look and see if that's the next one. But you can put other stuff in there too, not just numbers, like other functions. Like that's a thing that we're going to do a fair bit. Now, the other idea that I want to mention is the idea of inverse functions, which we're going to use a lot. And actually, hang on one second. I'm going to pause the recording here and go look something up. All right, I'm back. All right, I looked up what I wanted to look up, and I think I was about to go off on a tangent that goes in a different video, so we're gonna do that differently. So I wanted to talk about inverse functions and function composition. That's next video. What I want to do right now is kind of do some examples of messy looking functions and some stuff with graphs and tables and call it good. So let's call this function g of x equals x minus 3, let's do the square root of that, over x plus 2 times x minus 1 squared. I wanted to point out a couple of things that I can do here. So this is a bit of a mess, right? Like there's a lot of x's. And by the way, it's 100% fine that there's more than one x over here. Whatever goes in here just goes in for all of the x's. So if I wanted to find, let's say, g of, what do I want to do, like 12. That would give me the square root of 12 minus 3 over 12 plus 2 times 12 minus 1 squared. And we would simplify that, right? So the numerator there is the square root of 9, which is 3. And the denominator is, what's that, 14 times 121, whatever that is. I'm not going to worry about that. Right? Feel free to jam that into a calculator if you're interested in what the number is. I'm not. So the idea here is that I put in a number and it went in for all the x's, and then I got out some result. Feel free to calculate that if you want to. What I want to talk about very briefly are numbers that I can and cannot put into this function, because I can write any number I want in the parentheses, but not all of them will give me meaningful outputs. So for instance, let's say I tried to find g of 1. That seems like a, well, let's not do 1. Let's do 2. And then we'll talk about problems here. So I can get the square root of 2 minus 3 over 4 times 1 squared. 1 squared, and that will give me the square root of negative 1 over 4. Well, you may or may not be aware, but you can't take the square root of a negative number, or you can't do it without using complex numbers, which we're not going to do right now. So this is problematic. I don't want this, because I can't find the square root of negative 1, at least in the real numbers. And so I would say that I can't put 2 into g, right? I can write it in the parentheses, but the output that I get doesn't have any meaning for me. Similarly, what if I tried to do g of 1? I would get the square root of 1 minus 3. That's already a bad sign, right? That's the square root of negative 2. 1 plus 2 is 3. 1 minus 1 squared is 0. And so here I've got the square root of negative 2 over 0. So that's bad in 2 ways, right? So again, I'm trying to take the square root of a negative number, but that's not the one I want to talk about this time. The one I want to talk about this time is the 0 in the denominator. That's bad, right? You can't divide by 0. A lot of people mix this up with you can't divide 0 by things, which is not true. You can divide 0 into as many parts as you want. What you can't do is divide something by into 0 parts. That doesn't work. So these are the 2 most common problems with functions. And when we get to logarithms in the next section, I guess, not topic, but the next section of topics, we'll come upon some more. But basically, you don't want to try and take the square root of a negative number, and you don't want to try and divide by 0. Right? Those are the 2 major problems. So keep those in mind. I'm not just giving you oh, there's so many more problems. No. This is that. Just watch out for these 2, and you'll be fine. There are other things that can come up, but they're very rare. Don't worry about them for right now. Just these 2 for now. And then the last thing I want to talk about is what these look like on tables and graphs. So let me make a table here. So let's say I have this table, x, f of x. Right, so I've got an input of 2, negative 2, negative 1, 0, 1, 2, my standard 5 numbers. And my outputs look like this: 3, 1, 5, 2, 3. Okay, so this is 5 different points, right? That's really all an XY table is. It's just a list of points that are on the graph, or that are in your function. And so this is another way of saying that f of negative 2 equals 3, and f of negative 1 equals 1. I'm not going to write all of these, but I do want to do this one. F of 2 equals 3. Now, the restriction that I told you about for functions is that if you put something in, you have to get the same thing out every time. There's no, like, you can't put in 2 and sometimes you get 3 out, and sometimes you get 5 out, and sometimes you get negative 10 out. That's no good. It's got to give you the same thing every time. But is it a problem that when I put in negative 2, I got 3, and then when I put in positive 2, I also got 3? Is that okay? Is this still a function? The answer is yes. This is fine. You can get the same output for different inputs. What you can't get is the same input giving you different outputs, right? So this says that, did I, 4, 5, all right, so let's graph these. All right, negative 2, 3, there, minus 1, 1 is here, 0, 5 is up there, 1, 2 is over here, and 2, 3 is here. So the thing I want to point out here is this is totally fine. Any given x value gives me the same y value, or it only gives me one particular y value. The thing I was pointing out is this here, where different x values give me the same y value, but that's entirely fine, right? So think back to Santa's train machine. If Santa puts in a birch log, he gets out a train. If he puts in a eucalyptus log, he gets out a train. If he puts in an oak log, he gets out a train, right? So he gets the same output every time with different inputs, but that's fine. That's fine. The machine is still very consistent. It's still giving him, like, every time he puts in a birch log, he gets out a birch train. Every time he puts in a eucalyptus log, he gets out a eucalyptus train, right? So that's 100% fine. That's still a function. You only run into problems if you put in -2 and get out 3, and then put in -2 down here. So let's do this in a different color. Let's go purple. That's magenta, whatever. Let's say I put in -2 down here, and now I get out 7, right? This is a problem, right? This is not a function anymore because I put in -2 and got now 2 different things. One at 3 and one up here at 7. A smaller number, but there you go. Right, so that's no good, right? We can't have this and still be a function. We can have the same output though, that's fine. So that's how you can tell if something is a function from a table, is if the same input gives you 2 different outputs, but it's okay if different outputs or different inputs give you the same output. That's all right. That is a different property that we'll talk about when we get to inverses. And the last thing I want to talk about is something called the vertical line test, which I've actually already alluded to. Over here somewhere, yes. If you get points in a vertical line at any point on your function, or at any point on your graph, it's not a function, it's a relation, or it's just a relation. Or I should just say it's not a function. That's called the vertical line test, and it was here. You can zip back to this portion of the video where I was talking over this earlier to see why, right? Same x gives you different y's. That's what it looks like on a graph. So if I have, oh, come on, sorry, this is Zoom only accepts every other click for some reason. I don't know why. So if I have a function, or if I have a graph that looks like this, that is a perfectly good function because every vertical line that I draw will cross at only one point, right? Every one of those only crosses once. On the other hand, if I have a simpler looking graph, right, like let's say an oval, that's not a function because these vertical lines that I'm drawing hit more than once. Now, there certainly are vertical lines that you can draw here that only hit once, right? The ones that just like glance off the sides, but that doesn't matter. The only thing, like, it has to be a function at every point, not just at some points. So this is not a function, and this is a function. This is called the vertical line test. Vertical line test just checks to see if things are functions. Last thing I want to do. This. Let's say I have this graph. And let's say that this point is 0, 4. It's that point right there, and these are -2, 0, 2, 0, and then this guy right here is 3, -5. All right, so there's a variety. I know a variety of points on this graph. What I can do is so this graph's called. So I can say that based on the graph, because remember that a graph is just a big table. It's just an infinite table. That's all it is. But it's presented visually, right? This tells me that I could write a table out of this, right? I could say f of x looks something like this. I could say that if x is -2, f is 0. If x is 0, f is 4. If x is 2, f is 0. If x is 3, f is -5. Right? I can make that table of values. So this is some of the information that is contained in here. So let's say I didn't have that. Let's say I'm just going to select all this nonsense and get rid of it. And instead, all I had was this graph. I could say something like, find f of 2. right? Okay, well, f of 2 is 0 because this point is on the graph. I could also say find an x so that f of x equals -5. So what I'm saying there is, where's y -5? That's this height right here. So an x that does that is 3. Right? So if I ask for it, if I put a number in here, I'm telling you x and asking you to find y. If I say find an x, what I'm giving you is, so this thing right here, f of x is y. This says y equals -5. Find an x so that y is -5. Well, you look for where y is -5 and you find what x goes with that. So this is just a way of matching up x values and y values. That's really what this is. Or that's really all functions are, in fact, and it's all relations are too, but functions do it in a more consistent way. So that's the way you want to think of functions. There's some rule for taking the x's and telling you what the y's are. You put in the x's and you get out the y's, right? You can have that rule with, or you can have that rule given by a formula. You can have that rule given by a table. Oop, where'd my table go? I just skipped right over. You can have that rule given by a table. You can have that rule given by a graph, right? And that's sort of the key to function notation, is being able to read those things, being comfortable with those things. So that's what I want you to know about functions. We're going to talk about domain and range next, and probably some inverse stuff after that. So I will go ahead and stop the video here, and I will see you guys in the next one.